Okay, so welcome to Math219, and just for legal reasons, I'm going to go ahead and remind everybody we are recording this. I think the audio pickup is a pretty short distance, so I don't think most of y'all are going to be picked up by the microphone, right? But if you're close, that's possible, so be careful what you say. Okay, so let's hear real quick. So this is Math219. If you're here for a different course, you're in the wrong room. I've already gone through all of these introductory comments. I won't go through all of this again, but I do want to say, just as another reminder, I know you heard me talk about this a lot already because of the organizational video that I had y'all watch, but I think this is fundamentally important. This course is about ideas. Right, so make sure that you come into this with the right sort of point of view. That this is not about memorizing formulas and rehearsing algorithms, and that will be tested on your ability to regurgitate and perform rote tasks. Right, so we're going to be learning ideas, understanding how these concepts relate to these other concepts, and this kind of thing, reasoning, deductive mathematical reasoning, and comprehending how ideas relate to each other. That's what we're here for. Okay, all right, so enough of that, and I'm going to move on now to the introduction notes. Reminder, on the class website, right, there is a link in which I have all my course materials available to you all, including all of these notes. So make sure to have those downloaded or however you want to handle them. Okay, so I think it's good to start with the why are we here, right? Why are we taking multivariable calculus? Now I know that for a lot of y'all, the answer is because my major tells me I have to. Right? Okay, so let me then go to the obvious next question, which is why does your major force you to take multivariable calculus? Right? So I'm going to start off with what I hope is something you already believe, and that is that single variable calculus is important. Right? Y'all presumably all had a year, sometimes more, of single variable calculus, and you've seen bazillions of applications of various sorts. And now just to oversimplify and compact things down, derivatives and integrals, right? Y'all have seen a bunch of those, but in particular because derivatives are a tool that you use to understand how things change. So how's that for broadly applicable, right? Anytime something's changing, there's a lot of that in the world, right? So derivatives, clearly critically important to understand. Why are integrals important? What do integrals do? Common misconception is to think of integrals' job as to compute the area under a curve. That's a minor application at best. What do integrals do? They compute what I like to call accumulating quantities. Anything where you can break it up into pieces and the whole is the sum of the parts. Right? So area under a curve has that feature. The whole area is the sum of the areas of the little parts that you break it up into. So yeah, sure, but integrals can be used to compute so many more things. And again, you've seen a bunch of examples of applications of that idea in single variable calculus. So again, I hope that we're all sold already on this idea. Variable calculus is important. By the way, I have to force myself periodically to kind of pause, give you all a chance to sneak a word in edgewise, right? So let me pause here. Does anybody have any questions so far? By the way, I'll also interject. Y'all are very welcome to shoot up a hand, right? If you have a question or something like that, don't let the fact that I'm on a roll stop you. Okay, everybody's happy. Okay, so short answer, why is multivariable calculus important? Because the world's three-dimensional, not one-dimensional. Right? Three-dimensional world, single variable calculus means one-dimensional. Well, there you go. Now, so y'all have seen a bazillion applications in a three-dimensional world of single variable calculus, but in those applications, there were some very convenient assumptions being made about the nature of the question that basically kind of reduces it to a one-dimensional problem by oversimplifying. So let me just show you how that is Generically, not the case. So, for example, here's an idea of a derivative, a rate of change. Let's suppose you're in a three-dimensional context, as we often are. Here's u, right? And you're moving with some velocity. And you have some function that tells you what the temperature is depending on where you are in space. Now, this is not a weird scenario, right? This is extremely generic. Temperature varies depending on where you are, and I'm moving, all very real world. So how would I compute this derivative? How would I compute the rate of change of temperature with respect to time as I move in some weird direction, not parallel to one of the axes? Wouldn't that be convenient? Right? That's the kind of thing that they do in a single variable calculus class to make it kind of convenient. But just generically, if I'm moving off at some angle, how do you compute that rate of change? This is a multivariable calculus problem. This is the kind of thing we're going to be talking about in this class. Not today, later. Okay. Another example. If you have some lumpy thing, rock, kidney bean, whatever, right? And if the way mass is distributed depends on position. And y'all have seen some examples of this, but in every example you've seen in a Calc 1 class, Calc 1, Calc 2, the density only depended on one variable. Right, so you may have all seen the example of you've got a tank, right, and there's oil in the tank, but there's a certain amount of sludge in the oil, and so it's more dense at the bottom, less dense at the top, right? And you want to compute the total mass of oil or the amount of work it takes to pump the oil or what have you, right? Okay, well, the density only depended on height. Right? So real world now doesn't work out like that most of the time. So how in this scenario, with density depending on all three variables, now how would you compute the mass? Right? It's tempting to say, well, look at slices, but on that slice, however you slice, density is still not a constant. And so you can't just multiply size times density. So again, we're up a creek. How do we deal with this? Well, this is another multivariable calculus problem that we need to address. All right, how are we doing? Everybody with me? Okay, so these are sort of what I might call immediate applications of multivariable calculus. It's tempting to say, yeah, well, but so what? These are little trivialities of how do I compute the mass? How about instead of invoking big guns of multivariable calculus, how about I just put it on a scale? Right? I don't really need to know. This situation here, well, I'll use a stopwatch. Right? It seems like we can kind of handle this numerically. So where are some hard, real-world, challenging problems that we just can't get around without, with other methods? And so I've got several of them here. First one I'm going to talk about is economics. Now, might not be an econ major, but broad liberal arts education and all that. So here's how economists solve problems very often. They write down an economic model. And I just made this one up because the actual economics here doesn't really the point. Right? But an economic model might look something like this. It's an equation that involves a bunch of variables, a bunch of parameters. And notice that in this equation, I can't really solve for, I guess I could solve for Q. And I guess I could solve for K. But most of the variables in here you can't solve for. You just can't do it. Right? Now, how does an equation like this come about? How does, such an economic model? Well, these various parameters, it may be that there is some conserved quantity, right, that can't change. So you could have K can change and L can change and P can change, but there's some, immutable constant that is always fixed. And that when you write down the formula for that thing that has to be constant, it's this. Okay, fine, no problem. Here's where it gets weird. Let's suppose that I wanted to compute the rate of change of this variable P. How would I compute dp dt here? Now, a single variable calculus point of view would be to solve for P and then take a derivative. I can't solve for P, right? Look at this. The P, let's see here. This P here that I would like to solve for appears as a cube and as a linear and in an exponential. So game over. Forget about it. You're never going to analytically solve for P. So given that you can't solve for it, how could you even dream of computing its derivative? Does everybody see the problem? Okay. Well, it turns out that there is a way to address this. It's very clever, and y'all have seen a kind of a version of this in single variable calculus classes, but we're going to be talking about the more general version and the real version of what you've already seen in this class, and it's called implicit differentiation and the implicit function theorem, and it's a multivariable calculus thing. So if you want to be able to do economics, and I believe I understand some of y'all are econ majors, right? Multivariable calculus is essential to being able to answer standard econ questions like this. Pause. Everybody good? All right. Okay. I like to interject. I think this is a worthwhile comment. A lot of people think that there's no point in studying anything more than three variables. Actually, after all, we live in a three-dimensional world, right? So who cares about four-dimensional calculus? Why would I ever need to understand four-dimensional math? I'm not planning on going into a science fiction context or traveling faster than the speed of light or time travel, right? So why does four dimensions matter to us? This is an excellent little easy example that you got to keep in mind that variables are not all describing position, right? Variables can describe a lot of different things, and in economics they have a lot of parameters. What do I have here? 5 kind of what we call parameters, right? These are the 5, but then of course everything also depends on time, right? So this is a 5 plus 1 scenario, which if you want to keep it simple, there are 6 variables here. So when you answer a question like this, pretty standard econ kind of a question, kind of a scenario, you're doing 6-dimensional math, right? Does everybody buy it? Any questions? All right. Okay. Good news, you're not going to have to visualize 6-dimensionally, right? You can't. But I think it's important to recognize, though, that this idea that anything beyond 3 is pointless, or for mathematicians only, absolutely not. Okay, next examples. These equations right here, some of y'all may have seen these equations before, perhaps on a t-shirt. Anybody seen that t-shirt? Long story. This is 2 different representations of what we call Maxwell's equations. And if you want to understand electricity and magnetism, this isn't everything, but this is a lot of it, right? These are fundamental relationships between electricity and magnetism and understanding how they work. A lot going on here. So what do these things mean, right? So what's that thing? That looks kind of like an integral symbol, except there's 3 of them. What is that? What are we doing? Right? You taking an antiderivative 3 times? What? It's not clear what that is. How about that thing? It's a differential, but it's a vector, right? That's weird. So what does that mean? What about this thing here? That looks scary. What is that thing? What does it mean? So this is something that we're going to be learning in this class. And also I want to point out, understanding what the things mean is part of our goal, but I also want to understand, what does this equation really say? Right? And you can break that down into, well, just, sort of one little piece at a time, but but big picture, how should I think about these two equations? Not to mention the other six. How does this help me understand the fundamental quantities here? Oh gosh, let's see here. How does all of this help me understand electric fields? And how does this help me understand charge density, which is what that one there is? So there are fundamentally simple punchlines as to how you can think about what this stuff is saying. Right? So it's not just enough to know what the symbols mean. You need to understand, what are the equations saying? How best can you think about what those equations are saying, and what does that tell you about the objects that the equations are talking about? Is that cool? Now again, we're way away from this, right? This is going to be end of the semester kind of stuff, so don't worry about this right this second. Okay, let's see here. Last example. So if you're doing chemistry, let's say, and by the way, a certain amount of chemistry is just physics. Right? Kind of an example of that is, let's talk about molecular bonds. Right? So if you're studying chemistry, you're going to do a lot with molecules. Well, molecules are held together by bonds. What is that? How's that work? Are they little strings? Right? What is a molecular bond? Well, molecular bonds, in one form or another, come from the behavior of electrons. And so, okay, how do electrons behave? What is the equation that describes their behavior? And it's this thing. It's called Schrodinger's equation. This is an object of physics, quantum mechanics. Right? It's pretty scary stuff. And we're not going to do any of this in this course. Just to, I don't want to scare anybody too much. But if you ever do take a class like, PChem, Chem majors will take a PChem class, or certainly any physics majors will take a quantum mechanics class, and I think maybe even engineers have to take something that kind of, maybe kind of touches on some of this stuff here and there. You'll study Schrodinger's equation, and again, there's the question of what does it mean and how do you solve it? And ultimately, these are multivariable calculus questions. This is a multivariable calculus thing. This is a multivariable calculus thing. The function here that we're trying to solve for is, in a way, kind of sort of a multivariable calculus thing. Okay, so there's, of course, much more than just multivariable calculus to this, but it's a huge player in this question. So, easy examples of things that we need to be able to handle that I suppose maybe we could handle other ways. And then harder examples of things that we simply can't do without multivariable calculus, whether you're studying social sciences or physical sciences. It's really important to understand multivariable. So my last little pitch, why should we be interested in multivariable calculus? Why does your major force you to take multivariable calculus? It's because it's the calculus of the real world. So there you go. Y'all buy it? Okay. All right. Okay, so that said, let's actually start off on the process of learning multivariable calculus. Real quick, let me talk about the context. By the way, I believe I understand most, if not all, of y'all are not first years. This course has a linear algebra prerequisite. Practically no one comes in with credit for linear algebra. Historically, it used to be that multivariable calculus was taught first, and then linear algebra came after that. And there were really good reasons for this. some years ago, I'm going to say 5 because I don't remember exactly. It's in that ballpark. They switched, and we started doing linear algebra first, and then multivariable calculus second. So there's lots of complicated considerations on that choice as to which one should come first. But for sort of mathematical reasons, I mean, if we ignore the needs of the engineering school and the physics department and stuff like that, just purely mathematically, if you were a math major only and math was your only interest, and that's it, no question, linear algebra should come first. Because linear algebra is kind of a language that is the perfect language in which to discuss multivariable calculus. It just is. It's really, really handy, right? So make sure that you're good with what I'm going to call the basic linear algebra. Now, there's some far out linear algebra that we're not going to touch in this class. Jordan canonical form, never going to come up, not even a little bit, right? Let's see here. Well, anyway, y'all took an entire course. Most of it not really going to come up, but there are some parts that will. You'll notice here, by the way, I'm starting in Chapter 1 with Section 1.6, is because this has a kind of a review of linear algebra. And most of it, I'm going to leave for y'all to read on your own, remind yourself how all that stuff works. It's going to be from a different point of view because it's in a different book, of course. But make sure you're good with all the stuff in 1.6. These are the things that I feel it necessary to mention. Oh, and another little digression. In this class, there is too much stuff. We who would teach this course on a regular basis constantly complain about it, right? There's too much material. And there is a point of view that says this should be a full year course. And if this were a full year course, then it'd make my job a lot easier, right? I can kind of slow down, just kind of talk about everything. And sadly, I don't have that luxury. So because of how much material there is in this course, I'm going to have to make tough choices that I don't enjoy making. But I am forced by circumstance, again, to make these tough choices. And the tough choices are, what am I going to spend class time talking about? And what am I just going to have to let y'all read on your own? Right? So that is going to come up a lot. Now, I'll point out, this is actually not that rare. If you think about it, take a history class, right? And you have to read 200 pages of some history book, before the next class meeting. They're not going to talk about all 200 pages, right? They're going to pick and choose and say, well, here's an arc that I thought was interesting, and I want to explain as the instructor a certain point of view about. Notice how all of this is talking about. There's a common theme, or something like that. They don't actually walk through all the material. And so likewise in this class. So it's not that weird, but nevertheless it is a little, it's suboptimal, right? But it's unavoidable. I'm going to have to pick and choose. And so heads up. Do make sure that you read all of the appropriate sections of the book, because there will be stuff in there that just didn't quite make the cut on being class time worthy, but that is still fair game and that you're responsible for. You got to make sure you're good to go with. Okay. Again, pause. Everybody good? Okay. All right. So you may or may not have seen this one before. This is not a hard theorem to believe, but it may or may not have been covered in your linear algebra class, so I feel like it needs to get mentioned. It's called the triangle inequality for obvious reasons. And it basically says that when you add two vectors, which is where this little triangle of vectors comes from, that the hypotenuse, if you will, of that triangle, that length is never greater than the sum of the other two lengths. And from a geometry from a plausibility standpoint, I think this is a really easy pitch, right? I mean, the shortest distance between 2 points is a straight line. So green can never be greater than blue plus orange, right? So intuition-wise, this is, I hope, pretty clear. Is everybody happy with this? Okay. You can prove this by playing around with dot products and magnitudes and stuff like that y'all may or may not have done in a linear algebra class, but not what we're here for. Okay. Next thing. Now again, this one I hope you've seen. I know that you've seen how to multiply a matrix times a vector, right? That'd be a tough linear algebra class to teach without covering that. What you may or may not, but I hope you've seen, is this particular point of view on how to think about, how to interpret matrix vector multiplication. A lot of people learn that it's sort of dot product, that you take a row of the matrix and then you dot with the column vector, and that dot product gives you the first element of the product vector, right? So this is what I'm going to call the dot product point of view. Okay, this is a different point of view that gives the exact same result. So this is the same product, but just a different way of thinking about it. And that is this equation right here, that the matrix vector product is a linear combination. Right? That's not a dot product. That's a linear combination. It's a linear combination of what? Well, it's a linear combination of these things here. You'll notice are the columns of the matrix. Right? So it seems to be saying. So a matrix vector product is a linear combination of the columns of that matrix. And in particular, it's the linear combination where you use the coordinates of the vector as the coefficients in that linear combination. Is that cool? Show of hands, how many people have seen this before? Good, super, fantastic. Okay, this is also a nice example of what I was talking about earlier, that, look, answers are fine and all, but we're interested in ideas. And one of the things that I really like about this point of view on matrix vector multiplication is that it shows relationships between objects, right? So matrix vector multiplication is a concept that you can think about in different ways. Linear combination is a concept that gets used in various different contexts. Understanding a matrix as being made up of columns is a different way of thinking about a matrix. Typically, we think of a matrix as having entries that are elements. Right? Here, I'm thinking of it not as being made up of a bunch of elements, but as being made up of a bunch of columns of elements. Right? And so what we have here, this is a relationship between ideas, a relationship between concepts, you might say. And it turns out that this particular relationship between concepts is way more useful than the dot product point of view in a lot of circumstances. So again, it's not about the answer. I mean, now that very legitimate complaint could be made here. Yeah, but computationally, when it comes to plugging and chugging, this is a little bit more tedious to write down. That's fair, right? It is a little bit more tedious to write down. When you're coming to plugging and chugging, that's not what we're going to be doing. Right? So just, here's a matrix of numbers and a vector of numbers. Now do the arithmetic. Yeah, no, I don't even know that's going to come up at all in this class. Maybe once or twice. The point is the ideas and the relationships between them. How are we doing? Everybody happy? Okay. Cool. Okay, linearity. One of the fundamental concepts of linear algebra, right, is that we talk about, among other things, functions that are linear. Now, y'all presumably saw general abstract linear transformations, we're going to focus our attention on what I like to call Euclidean linear transformations. In other words, linear transformations where the domain is Euclidean space and the target is Euclidean space, of different dimension perhaps, right? But just Rn and Rm, none of this funny business about, well, let's consider the vector space of all solutions to a certain differential equation, right? Nothing like that, nothing abstract. Okay, so Euclidean only. That said, a function is linear if it satisfies this equation for all vectors and all scalars. Hope that looks familiar? Yeah? Everybody seen this before? Cool. The way I like to think about this, it's just my favorite point of view, is if you do a linear combination, namely a sum of scalar multiples, before you plug into the function, versus if you do a linear combination, namely a sum of scalar multiples after you plug into the function, linearity says that you get the same thing both ways. And then just casually, sort of conversationally, I like to describe this as a linear function plays nice with respect to linear combinations. Do it before, do it after, whatever, it's all good. That make sense? Okay, so really important idea to understand what is linearity. Now, of course, there are these alternative ways to think about it. They're all equivalent. Take your pick. There are some circumstances where what I have written here is really the most convenient one. There are other circumstances where maybe this one or maybe that one are, depending on the circumstance, more convenient. Right? So it's really important to be comfortable with not only all three of these points of view, but please also make sure you're comfortable with why they are equivalent. You know what? I shouldn't have. That was. Let me just get rid of all this. Why is? You know what? Let me do it like this. Actually, why is 1 equivalent to 2, and why is 2 equivalent to 3? Right? Those are good questions to make sure that you're good with. So if that rings bells, and if you're quite sure you remember from linear algebra class why these are all equivalent, cool. If not, this is a good one to think about. By the way, this kind of thing, this is going to happen a lot in this class, where I'll point to something. Oh, by the way, make sure you're good with such and such. Right? And if you're not, fantastic question for office hours. Please just keep track of these little exercises, unofficial exercises that I throw out. And if you're not sure how to do them, or if you can't remember, or I don't know how to get started on this, drop on by office hours. It's a great thing to talk about. Be happy to have. All right, is everybody happy? Yeah.
When is your office hours?
Oh, that is a great question. I don't remember. So I'm going to show how to answer the question. So again, class website, right? This is for our section. But office hours are on the course website because they're shared, right? So y'all are welcome to my office hours. You're also welcome to Professor Hughes's office hours. And you'll see down here, kind of bottom right, if you will, and apparently my office hours are Monday, Wednesday, Friday, 11:20 to 12, and Monday, Wednesday, Friday, 2:40 to 3:10. Do note the different locations. These first hours are in my actual office. My second hours are in this room because I'll be teaching a class right before and a class right after, and so I'm pretty sure there's nothing scheduled in between, and so what's the point of me lugging all my stuff downstairs? There's just no point, right? So I'll be in here. Okay, good. Is everybody all good? Okay, all right. So, yeah, moving along. Now, y'all have seen linear transformations before. Again, linear transformation is just fancy talk for a function that's linear. That's it. So here's some examples. And again, I hope you all may have seen this kind of thing before, but given a fixed vector A, so that's not a variable, that's fixed. That's just it's a vector of constants, not allowed to change for the purposes of this conversation. And that said, the function that acts on a input vector x by dotting with that fixed vector A. So this, what I have circled in green, the action of dot product with this fixed vector A, that function, green, that function is linear. Does that look familiar? I hope. If not, easy to check. Right? You can just take the definition that we were just looking at, definition of linearity. Here is a function for which you have an explicit formula, and you can just directly confirm using known properties of the dot product that indeed this satisfies those linearity requirements. Y'all feel okay with that? All right, now casual parlance. Colloquially, we'll say the dot product is linear. Now that's an abuse of terminology, really. The dot product is an operator. It's not, we don't really think of it as being a function. So when I say the dot product is linear, what I mean is the dot product thought of as a function of just one of the input vectors with the understanding that the other input vector is fixed in order to make dot product understood as a function is linear. But that's too much to say every time. And so casually, we say dot products are linear. Is that all right? Okay. Likewise, cross products are linear. Same discussion of terminology. So a little bit weird, a little bit stranger. Frankly, cross products are kind of weird, but anyway, also linear, as it turns out. Okay, here's the one that tends to throw students for a loop. Understood appropriately, there is a linearity of sorts that relates to determinant. Now, we've got to be careful with this. This thing that I'm saying is linear, right? Now I don't want to make a check on that yet because I want to make sure to define what it is before I go around making claims about it. This thing is not determinant. Determinant acts on a matrix, right? If you want to take a determinant of something, you can't take the determinant of a vector. You can't take the determinant of a bicycle, right? You take the determinant of a matrix. Determinant as acting on matrices is not linear. But if you fix all of the rows of the matrix except for one, right? Now think of the function that acts on just this last row. That's it. Right? So the first n-1 rows are fixed constants, not allowed to change at all. Think of determinant as something you do once you plug in that last row. Now I have a function that acts on a single row. And this function is linear. And y'all may have seen this fact. I hope y'all have seen this fact before. I'm sure that y'all have seen facts similar to this. You've probably seen that, if you multiply row operations, right? Y'all have seen row operations. If you multiply a row by a scalar, that scales the determinant correspondingly, right? That's part of linearity. That's we're halfway there, just that one property. So in general, though, one row at a time, determinant is linear. And in order to avoid confusions, they made up a new word to describe this property of determinant. By the way, it doesn't apply just in the bottom row. It also applies in any row and any column. So this property of determinant is called multilinearity, because of how it is a linearity that applies in multiple different ways. Interpreted suitably, of course. How are we doing? Is everybody okay? By the way, I think this is an underappreciated fact of linear algebra. There are linear algebra classes, possibly ours, I don't know, that don't talk about multilinearity. I think that's unfortunate. Multilinearity is really cool. It's really powerful. Very, very useful in a lot of ways. I think it's worthy of mention. So anyway, that's part of the reason I included it here. Okay. All right. Moving along. More facts. Oh, let's see here. By the way, it is 11 o'clock. I have until 11:10, I think. Okay, all right. So more facts. Roughly speaking, what I'm going to interpret this statement as saying is that linear transformations are matrices and vice versa. We have to be careful with how we phrase that. I do emphasize that I'm only talking about Euclidean functions. So only Euclidean, yeah.
What's the backwards case?
Oh, yeah, thank you. Yeah, I appreciate that. I very often use standard math notation and forget that not all of y'all have seen these things. So this little backwards capital E is not, like Russian or something. This is a little mathematician shorthand. Maybe it's Russian. I don't know. It doesn't come from the Russian, though. This is just a mathematician shorthand for there exists, or there is, or something along those lines. So yeah, it's just a convenient notation. Okay, so we're going to talk only about Euclidean functions, and when we are given a matrix, we're going to understand the matrix as being a function in this, I'm going to say, pretty standard way. If someone gives you a matrix and says, hey, make a function out of that, well, okay, take that matrix and multiply by the input vectors seems to be a pretty natural, pretty believable, I hope, obvious, simple, convenient way to make a function. And that's what I'm going to be. When I say a matrix is a function, this is what I mean. Right? Okay. So all of that said, this statement here simplifies very nicely as every linear transformation is a matrix, and every matrix is a linear transformation. In the Euclidean context, linear transformation and matrix, they're, I don't want to say quite the same thing. They're different as objects, right? One's made up of a bunch of numbers. One's a function, right? So they're different in that sense, but they're interchangeable. Every one of one is one of the other, and vice versa. Have y'all seen this fact before, perhaps? So this is one of these ones that maybe, again, underappreciated. Willing to believe that this may have been in your linear algebra class, but perhaps not emphasized. But it is really important for what we're going to be doing. So I'm going to walk you through how to see this. Why is it that every matrix is linear transformation and vice versa? Well, the upward, given a matrix thought of as a function, how do I know it's a linear transformation? Plug and chug. Y'all can totally do that one, right? Just go through and plug in this function into the definition of linearity. And just compute both sides and notice they're the same. All right. Going the other way is where it gets tricky. Supposing that you have a linear transformation, how do I know that there is a matrix that describes that linear transformation as a function in this usual sense? I mean, where does this matrix come from? I've got a linear transformation. How do I make a matrix? And there's a lovely little argument here. Here's the basic idea. I'm going to start off real quick, little side note, that when you have a vector, you can view this vector, any vector, as a linear combination of standard basis vectors. So this is x1 times that vector that's all zeros, except for a 1 in the first position, and then plus et cetera, et cetera, et cetera, and then finally xn times the vector that's all zeros except for a 1 in the last position. And the shorthand for this is to say that x as a vector is x1 e1 plus ... plus xn en. So this is just a very convenient little notational shorthand. What I have circled in green here, these are called standard basis vectors. This little e with a subscript notation, very convenient. You're going to see that in a lot of places. Sometimes these are called ij and k, right? Because they're parallel to axes, magnitude 1, right? And they come up a lot. They're very useful, very fundamental. But I like this standard basis notation with e's and subscripts because now I'm not restricted to just 3. And again, 3-dimensional is really not good enough. Right? We saw that easy example of an econ example where, we had 6 variables. And so what are you going to do? I, J, K, L, M, N. What if you had 47 variables? You're going to run out of letters. The whole thing becomes silly. So this just makes life easy. How we doing? Is everybody on board? Okay. Well, with this noted, this equation, let's see here, hang on. This equation right here, sorry, my elbow sometimes hits the little thing. If I just rewrite a vector x as a linear combination of standard basis vectors, then the linearity, whoops, I wanted a highlighter, I'm sorry. Sometimes I fumble with the thing here. Linearity, right here, tells me linear combination on the inside. I can just as well do the linear combination on the outside, right? And having done that, let me clean up my mess. I have a linear combination, you'll notice, of images of standard basis vectors. And now let me say that again. Linear combination of images of standard basis vectors, and there's a knee-jerk reaction that I have in my head, and I hope you all will eventually develop this same knee-jerk reaction. Whenever you hear linear combination of, I hope you'll be reminded of this fact right here, that a linear combination of columns is a matrix vector product. And you'd be surprised how often this is a handy little connection to make. So I don't have here a linear combination of columns. I have a linear combination of images. But if I were to take those images and make them columns, now I have a linear combination of columns. And a linear combination of columns is a matrix vector product. Right? Does that make sense? So it's a clever trick. Reasonable, I think, to judge. I'm not sure if I ever would have thought of doing this little clever trick, right? But just make sure to realize you don't have to have thought of this clever trick. I'm showing you the clever trick, right? And by the way, I didn't think of it either. Somebody showed me, and I'm pretty sure somebody showed him. Right? So this traced back to some super clever person who thought of this the first time, but that's not our responsibility. So all we have to do is understand, having someone else having showed us the trick, understand how the trick helps us turn the theorem as it is. And so here's our result, as intended. The linear transformation can be computed with a matrix. Okay, so really important fact, really important proof. A lot of good ideas floating around in this statement, and so I want to make sure you all are comfortable with all of the ideas in this argument, but also, very importantly, if you have a linear transformation and you want to write that linear transformation as a matrix, the matrix is the, well, let me do it like this. The matrix is the matrix whose columns are the images of the standard basis vectors. Really, really important. Oh my gosh, so important. When you have a linear transformation in Euclidean space, those columns are the images of the standard basis vectors. Let me say that a little bit differently. If you have some linear transformation and maybe you don't know the formula for the linear transformation, maybe it's just described geometrically like a rotation, like rotating around the origin, right? That's a linear transformation, but how do I write down a formula for that? Oh, well, if I just look at these standard basis vectors, see what my linear transformation does just to the standard basis vectors, I can make those the columns of a matrix, and I'm in business. Really important fact. Okay. Let's see here. This would be a good place to end it. I know you all know how to multiply matrices. Again, I want to remind you there are different ways to think about it. You can do the whole dot product point of view, and that's nice for plugging and chugging. Again, that's not really what we do here. Make sure, if you would, that you also understand the linear combination of columns point of view on matrix multiplication. And there's also a linear combination of rows point of view on matrix multiplication. They're both important in various different circumstances. But anyway, what I want to focus on here is that when you multiply matrices, you are effectively composing linear transformations. Right? So anytime you have a linear transformation, you've got a matrix. Well, the action of composing the transformations is equivalent to the action of multiplying the matrices. This is not obvious. This is wonderfully, conveniently true, but why this works is a long conversation. Okay, how are we doing? Is everybody happy? We are out of time. Nice to meet y'all. Look forward to seeing y'all throughout this semester. Have a good one. See you on Wednesday.